All right, good morning. We'll go ahead and get started today. So in the textbook, you should be reading chapter 4 now. So the lecture will start going into the contents of chapter 4. Don't forget that the homework for chapter 3 will be due on Friday. So to start off with chapter 4 material, there's some notes about matrices that are important. So we will be working with matrices that are known as square matrices, where the number of rows is equal to the number of columns. And the structure of square matrices can allow you to work out matrix multiplications more quickly if they are block diagonalized. So let me show you what that looks like. So multiplication of square matrices. So let's suppose we want to multiply a 6 by 6 matrix with another 6 by 6 matrix. All right. So maybe we'll write out a matrix where we have some values here that are non-zero, and I'll just put number. So that the first row elements of the matrix will be 2 numbers and then zeros afterwards. The second row will be 2 numbers and then zeros afterwards. And then let's say the third row of the matrix has a number in this position and all zeros elsewhere. And then the last 3 rows of the matrix, let's say that they look something like this. Then you have a number, 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 some number here, some number here. So here's one of our matrices. Now, all of these zeros obviously give zeros as products. But what's interesting, if we look with respect to the diagonal, there are blocks that represent square matrices within this larger 6 by 6 square matrix. So, for example, right here, you have a 2 by 2 square matrix. And then right here, there's a 1 by 1 square matrix, right? And then down here in the bottom is a 3 by 3 square matrix. So if I multiply the 6 by 6 matrix with another square matrix that is 6 by 6, which has the same structure, then it's very easy to multiply. And this is called block diagonalization. All right, so I make blocks of square matrices along the diagonal. And all I have to do to multiply the large matrices is just multiply the small block matrices within. So you have another matrix here with the same block structure. Right, so there's the 2 by 2, the 1 by 1, and then the 3 by 3. So the matrix multiplication, you just take the 2 by 2 block matrices and multiply those. So you should generate a 2 by 2 square matrix. The other elements are going to be 0. outside of these blocks along the diagonal. You multiply the 1 by 1 to generate another 1 by 1 matrix in the middle, and so on. Here's the 3 by 3. To generate another 3 by 3 matrix. So you can take large matrices and simplify the problem considerably if you have a structure where you have zeros off the diagonal that lead to square matrices with some non-zero values along the diagonal. Okay, so it's a useful trick. Any questions on that? Pretty simple idea, hopefully. Another idea that I want to mention is there's the values along the diagonal of the matrix. If we take the sum of those values, that's known as the character of the matrix. The sum of the values along the diagonal of a square matrix is its character. A lot of times in the textbook you'll see that abbreviated with a chi for character. And so when you see that symbol, we're just taking the sum of the diagonals. Okay. So just two quick notes about matrices to get us started in Chapter 4. Any questions about that before I erase it? All right, so we've just learned about the point groups, the chemically relevant point groups back in Chapter 3, and everybody should be working on identifying, assigning point groups to various molecules and getting faster and faster at that exercise. Associated with those point groups, of course, you have various symmetry operations as elements in the group. So for example, I could take just your point group C2V, and we know that the symmetry operations are identity, C2, and then we have two vertical planes, which we can just assign sigma xz, sigma yz, right? So those are symmetry operations in C2V. They give rise to the elements of the group. All of these elements are in their own class in this particular case. When we work with point groups, we will be in the habit of grouping together the symmetry operations or the elements of the group that are in the same class. Okay, so in this case, everything is in its own class, makes it pretty straightforward. So the next thing that will be important for us as chemists is to understand the idea of representations in point groups. So I can use some sort of a basis. I need a basis for creating a set of matrices so that we understand how those matrices transform with each of these symmetry operations. And so we've started to see now some instances where we write transformation matrices. That is to show how points move in Cartesian coordinate space when we perform some sort of a motion or a symmetry operation, more importantly. All right. There are all sorts of possibilities for what one could choose as a basis for making a representation within a point group. So you could have lots and lots of bases. For example, we could take X, Y, and Z, as a basis. Right, so this will be more or less familiar to us because we've started working with moving points in space. So if we take a representation, and I might use the capital Greek letter gamma here to represent representation, and I'll just give it a subscript x, y, z, so that just give me some sort of a note as to what is the basis for this representation, right? So then I can write matrices for x, y, and z as they transform with each one of these symmetry operations, right? So we know that with the identity operation, the transformation matrix should look like this, such that if I multiply by the points x, y, z, I regenerate x, y, z, and I have not changed the point in space, right? That's the identity operation. Now notice, I have a square matrix here representing the transformation of the basis as a result of the action of that symmetry operation. So if I take the sum of the characters along the diagonal of this square matrix, I notice that chi is equal to 3. Okay? So in this way, I've now generated the first value for this representation, 3. So under the identity column, the number within that representation gives you the dimensionality of that representation. So this would be said to be a 3-dimensional representation. If the value here was 1, it would be 1-dimensional, and so on. Right? So this is the dimensionality of the representation. All right. Now if I work with C2 symmetry operation, the transformation matrix, because the convention is to align C2 along Z, right? If you want, you can put Z here as a subscript to indicate specifically the orientation of that C2. X and Y will go to their negative after the 180-degree rotation. So these values are -1. And then Z is unchanged. So that the transformation matrix looks like this, right? And then chi is now -1. Does that make sense? So I can put this value here. And then for sigma xz, I can work similarly. We know that y will be carried to its negative after reflection about the xz plane, but x and z being in the plane are left unchanged. So we have something that looks like this for the transformation matrix. Okay? So in this case, chi equals 1. And then I work out the transformation matrix for sigma yz. And now y and z are unchanged, but x is reflected to its negative. And then chi should be +1 again. Okay. So we've now created a representation within this point group C2V. Okay. Now, one of the rules of your point groups is we've learned that we can identify conjugate elements of the group, and conjugate elements of the group are put into the same class. All right. That means in relation to the characters of the representation, every one of the symmetry operations within a class must have a transformation matrix that generates the same character. Okay. Now here we don't have to worry about that because everything is a class of order 1, so we don't have to worry about that. But we'll see lots of point groups where we have greater than 1 order of the class. And so every symmetry operation must have the same character for its matrix. That is a rule that must hold true. Okay. Notice that these transformation matrices can be block diagonalized, right? So these can be broken up into a series of 1 by 1 blocks. And in fact, one of the things that we can see from this is if we just took one-dimensional bases for the representation to make a one-dimensional representation, we would have the characters of the corresponding matrices for each of the symmetry operations. So what it means is I could just take X as a basis for a representation, right? You could take anything as a basis for a representation. Let's say I have a C2V point group. I could take any 2 points in relation to the origin. Let's say this is the origin, and I have space that goes like this. I could take any 2 points I wanted to as a basis for a representation and call those 2 points together as one object. And maybe to make that more sensical, I could just make a weird worm shape. And I could ask myself, is this a basis for a representation in that point group, right? If I rotate about Z, I don't generate a symmetry equivalent image at all if I generate reflections. So some things can be a basis for a representation, but not everything. But there are lots of possibilities for how to generate representations in point groups. And that may sound really weird at first, but we'll start to see how this applies in chemistry. Certainly the functions x, y, and z, which are basically in relation to the p set of atomic orbitals, can be used as a basis for a representation, which have these characters in the C2V point group. So we can use atomic orbitals as a basis. We can use chemical bonds as a basis, and other things, right? Let's say we have a molecule water, and I orient the oxygen of the molecule water on the z-axis. The plane of the molecule is the xz plane, right? And I could take as a basis for this representation maybe small arrows at each atom. Maybe an arrow that goes x, an arrow that goes z, and an arrow that goes back, and we'll call that y. And on this hydrogen, maybe we can call this x, we can call this z, and we can call this y. And same thing here. So if we use these 9 little arrows as a basis for a representation, we would have a 9-dimensional representation. You would have a 9 by 9 square matrix where you would assign each one of these a row column value. You could say x1, y1, z1, x2, y2, z2, x3, y3, z3 if you wanted to. And then you want to show how these points transform with various symmetry operations. Okay? If the component of the basis moves to a completely new location, then its value will be 0 in the symmetry transformation. If the point or the component of the basis remains unchanged in space, then it gets a 1. If it stays in the same place but goes to its negative value, then it would have a component of -1, right? So don't want to erase this because I was going to. I need board space. If we take C2 and try to write a 9 by 9 square matrix, right? So we say the values are x1, y1, z1, x2, y2, z2, x3, y3, z3, x1, y1, z1, x2, y2, z2, x3, y3, z3. Right? You could make a 9 by 9 matrix for the C2 operation. So if I have x1 and I perform a C2, so these are the ones, let's say these are the 2's and these are the 3's. Notice the hydrogen atom 1 whips over to this side, and so the vector x1 is not in the same place. It moved, right? So it contributes nothing to the character of that representation, right? We're only interested in the diagonal terms in determining the characters. The y1 also moves out of position and contributes nothing to the character. And the z component also moves to a new position. So those contribute nothing to the character in the representation, right? And then similarly, everything on hydrogen atom 2, upon performing the 180-degree rotation, moves over to this position. Those contribute nothing to the character as well. It's only the x, y, and z little arrows on the oxygen atom, which are on the C2, which will contribute anything to the character in this matrix. And so x will move to minus x. So this term is minus 1. And then y will become its negative. So the term here is minus 1. And then z remains unchanged. So its character is 1. So then the character of the overall matrix is minus 1. Okay? So you can work out the characters for very large multidimensional representations by taking the sum of the terms on the diagonal of the square matrix, that's the transformation matrix, for that basis in the specific point group that you're working. Okay? So you could do this for the other two operations. If we take this molecule again and work out the character for the 9-dimensional representation in C2b, with the xz plane, all 3 atoms are in the plane, which means all 9 vectors will contribute to the character because they stay in place, right? So it's only the x and z's that are in the plane. And there's 2 x and z's for each atom, so those will each contribute 1 to the character, or plus 6. And the y's go to their negative after reflection about the xz plane. So those each contribute minus 1 to the character, so that altogether character should be plus 3. Sorry. And then if I take the mirror plane YZ, notice when I perform that reflection, these 2 positions exchange, so none of those small arrows will be in the same location. They contribute nothing to the character. In other words, they have an off-diagonal element, right? With the YZ, the X1 will go to minus X2. So X1 would go to minus 1 here. So it's an off-diagonal value. We don't count that in the character. So anyways, the YZ plane, we don't worry about these. We only have to worry about the 3 small arrows located on the oxygen, which is on the YZ plane. The Y and Z arrows are in the plane. They each contribute 1 to the character. And then the X will be reflected to its negative, so that contributes minus 1 to the character, so that overall the character is 1. Okay. So now what I've shown you is how to make a 9-dimensional representation using what happens to be these 3 little XYZ vectors on each atom in a molecule of water as a basis for a representation that have the characters 9, -1, 3, and 1 in the point group C2b. Okay. So then one question you might have is, well, how many of these can I write? You could write lots of them, right? It turns out that there are certain fundamental representations that are known as irreducible representations. So, versus reducible representations. Okay. Over the course of the week, we'll introduce a formula that will allow you to determine whether a representation is reducible or if it's one of the fundamental irreducible representations in the point group. All right? In order to work that out, we need to know a few rules about the irreducible representations in point groups. Okay? Before we get into that, I know this is kind of new, generating a matrix, determining the character of the matrix so that we can produce representations in a point group, right? We have to wrap our mind around that idea. So I want to just stop here for a moment and just give you a chance to ask questions or probe this idea a little bit here in class. Yep.
So, why is there 9? Like, do you do 2 or do you do 4?
Yes, that's a great question. Why is this representation 9-dimensional? The only reason it's 9-dimensional is because I had a basis, and I just plucked this out of thin air, which has 9 pieces to it, right? So I made these 9 little vectors, x, y, and z, where they emanate from the centers of these atoms in the molecule. And so I just made it up, a 9-dimensional representation. And one of the reasons I made it up is because it has chemical relevance and it works out as an actual representation in the group. But you said, could you have something of order 4? So, yeah, we could try to come up with something for 2, right? Let's see what that looks like. If I just work with water again, I could pick the 2 OH bonds as a basis for the representation. Okay. So if I have 2 OH bonds, we could call this alpha 1 and alpha 2, I don't know. So alpha 1, alpha 2, alpha 1, alpha 2. Or I guess if I want to write it like this. The representation will be 2-dimensional because I have 2 entities in my basis for making this representation. So you can pick any n-dimensional object you're interested in. So one of the things you asked about is, can you have representation of order 2 or dimensionality of 2? So here's one way that you could do that. So because with identity, these 2 remain in their position, the transformation matrix looks like this. The character equals 2, the sum of the terms in the diagonal. So that's how I come up with this number. Okay? So then I can write a transformation matrix for C2 like this. And notice that Alpha 1 goes to alpha 2. It doesn't go to itself. And then alpha 2 goes to alpha 1. So I have a transformation matrix that looks like this. And now I have no diagonal term. So chi is 0. I guess I have diagonal terms, they're just 0. The sum of them is 0. The character is 0. So what this matrix tells me, if I take these row elements, remember, and multiply into these column elements, I see 0 times alpha 1 plus 1 times alpha 2. So I get the term alpha 2 here. And then 1 times alpha 1 plus 0 times alpha 2, which means I end up with the product matrix that looks like this. So this tells me that the C2 takes alpha 1 to alpha 2. Sorry, that should be a 2. And it takes alpha 2 to alpha 1. And that's exactly what a C2 does, right? And then I do the same thing for the mirror plane sigma xz and the mirror plane sigma yz. So if I take sigma xz, excuse me, the whole molecule is in the xz plane. We get to choose that. If you wanted to, you could make the whole molecule in the yz plane. You get to set the Cartesian coordinate system however you like, right? So we just set it up in a way that makes it easier for us to solve the problem. And if we set one of the axes so that the molecule is in one of these vertical planes in C2V, it makes it an easier problem to visualize. Okay? So that X is by choice for those reasons. Everything, all the bonds are in the plane and they stay in place. So I have a transformation matrix that looks like this, so that the products here are alpha 1, alpha 2, like this. Right? This row times this column, alpha 1. This row times this column, alpha 2. Points are unchanged. That's consistent with what's happening when I performed a reflection about the XZ plane. The character of that matrix, the sum of the terms along the diagonal, is 2. So that goes right here in the representation. And then if I work this out for sigma yz, now the reflection about the yz plane will exchange alpha 1 and alpha 2. So the transformation matrix looks like this. The sum of the terms on the diagonal is 0. So the character is 0. And then that completes the representation where I use the OH bonds as a basis for constructing the representation. Okay? Let's erase this. And if you wanted to make a 4-dimensional representation, you could do that as well. So I guess one way that you might decide to do that, and there are other things that you could choose as a basis. Let's say I keep water, again, as a way to confine myself to the C2V symmetry. Let's just take 2 arrows, and let's make one go like this, and one go like this. And then we'll do the same thing here. One go like this and one go like this. And we can call this A1 and B1, and then this one we call it A2 and B2. So I'm just completely making this up, right? So I've got 4 little arrows. That will be the basis for a new 4-dimensional representation, so that if I write the column matrix for these 4 items in my base as a basis. I have A1, B1, A2, B2. And this will make a new column matrix with these four components of the basis exchanged in some way. And so now I need a transformation matrix. So for the identity operation, it should look like this. Because this, whoops, I got sloppy there. This transformation matrix will take, notice I take each row here and multiply it into the column matrix. Every value in this column matrix is identical to the product matrix. And then the sum of the terms on the diagonal is now 4. And that's the dimensionality of the matrix. Okay, so there's a 4-dimensional matrix that we're starting. This will be a little trickier. So let's take C2. Notice C2 is going to exchange the positions of the hydrogens, so that A1 would go to A2 and create an off-diagonal term. So I would generate a 1 here, so that this row, when multiplied into the column, gives me an A2, which is what happens when I perform C2. A1 goes to A2, right? For the B1, it's going to exchange with B2, so I need to have a term that looks like this, or sorry, row elements that look like this, so that I get B1 going to B2. A2 exchanges with A1, so I should get these terms in my transformation matrix, so that when I multiply here, I get A1 there, and then B2 and B1 exchange, so I should have 0, 1, 0, 0. So I take those row elements, multiply into the column matrix, I get B1. So B2 transforms to B1. Okay? And I see that with this basis, the character is 0 under the operation C2. So this seems kind of weird. It's definitely kind of abstract. You're wondering, why is this important? That will come later. If we understand how to make the representations, that will be very helpful. And we'll do more of these this week, so don't worry if it's not falling into place on the very first day that you're seeing this stuff. All right, so if we take sigma xz, the plane of the molecule, everything is in place. We know that A1 goes to A1, B1 goes to B1, A2 goes to A2, B2 goes to B2. So your transformation matrix basically looks like that of the identity operation. And characters 4. Okay? And if you see something that's not making sense, tell me to stop, and I'll stop, and I can just kind of go through that again. And then if I work the character for sigma yz, sigma yz will exchange A1 to A2, B1 to B2, A2 to A1, and then B2 to B1. Right? And that's basically what the C2 was doing. So I should have 0, 0, 1, 0. And then B1 goes to B2, 0, 0, 0, 1. A2 goes to A1, 1, 0, 0, 0. And then B2 to B1 is 0, 1, 0, 0. sum of the terms on the diagonal is 0. So this becomes 0. And now I've constructed a 4-dimensional representation. Okay. Now notice with the 4 representations I made here, I don't see the same block diagonalization structure as I did with my first representation. Got 10 minutes. Right, I cannot block diagonalize this into 1 by 1 or 2 by 2, even 3 by 3, right? I can't simplify that matrix because of these off diagonal terms. Okay. The matrices here have this similar block structure throughout, and it turns out that I could use either X, Y, or Z as a basis. So if I take just Rx, a representation where X is the basis, and in my molecule, I can represent that with something on the oxygen atom, a vector, say, pointing in the X direction. Right. So I need something that's on the C2 axis, just representing the X direction. So I'll make a 1-dimensional representation with the identity operation. Nothing happens to this vector. If I perform a C2, this goes to its negative. I have -1. And if I perform the sigma xz, nothing happens to the vector. If I perform a sigma yz, the vector goes to its negative. It's in the same position, but it goes to its negative. All right? And notice the characters are the same as what we see in these blocked out matrices for the higher order representation of 3 dimensions. So this will show us that some representations that we construct can be broken down into simpler representations, irreducible representations. This cannot be broken down into any simpler units. Yep.
In the last case, when the x goes to the negative direction, why isn't it 0? Why is it -1?
It's 0 when it moves to a new point in space. So that's why I drew the X on the oxygen. If I had drawn as a basis an X vector on this hydrogen, then when I make a C2 operation, it moves to a completely different point in space, so it's 0 contribution to the character of the matrix. Okay? It moves way out over here somewhere. So it only works when I put X somewhere along the C2.
So if our basis is X for hydrogen, then it should be 0.
Right. And so it's possible to make representations that are not real, that are, trying to think of more precise wording. You can make up representations that are not allowed. So that's a pitfall that we'll want to avoid. So if I try to make a representation with this X vector on the hydrogen atom, I would have, let's erase this. So here's X on the oxygen. Here's X on the hydrogen. So is this a basis for a representation? That's the question we face. Because I can imagine an infinite number of possibilities, right? I could come up with this worm shape. Are these bases for representations? Sometimes they are not. And the symmetry operations will actually tell you if it is or if it isn't. Because the fact that I move here to maybe to simplify this a little bit. Since there's no symmetry equivalent on this side, I have a problem. Every symmetry operation should generate an image that is a symmetry equivalent. If I perform a C2, so I'm looking at it, I see X is going this way on this point. I look away, you come over here and do a C2, I look back, and I see something that looks like this. Something's changed, right? So it's telling me there's something wrong with using this only as a basis for the representation. If I try to write the characters for this proposed basis, C2 takes this to a new point in space, which contributes nothing to the character in the transformation matrix. And there's no other dimension I have to work with. There's no other component of the basis. I'm just left hanging there with a 0. Okay? Now if I do sigma xz, I get 1 because this is in the xz plane. If I do sigma yz, I have the same problem. I move to a non-symmetry equivalent position without anything else in the basis. So I have this representation 1, 0, 1, 0. Is this a representation in C2V? Now I have not given you the rules of irreducible representation, so you don't yet know how to deduce that more rigorously. But the fact that this symmetry operation, say C2 or sigma yz, didn't produce the symmetry equivalent image is telling you that there's something wrong in a qualitative way. All right? What we'll do on Wednesday is I'll give you the rules that govern the properties of irreducible representations in a point group, and then we'll have a better way of being able to say whether or not something can be a basis as a representation in the point group, and we will learn how to deduce all of the irreducible representations in a point group, and we will learn how to convert reducible representations to the irreducible representations. So that's kind of the preview of what we'll see the rest of the week. So we'll do that on Wednesday. And that's a perfect stopping point. So y'all did great today. You asked good questions. Anything else before we take off? So I'm going to write an X by this, not a representation. Stay tuned. Yes?
I have a question regarding the exam.
The exam? Okay.
So, maybe when we are trying to designate the characters we're going through, and maybe we have like 25, and maybe the person just missed 1, is the person going to result in 1?
You can get partial credit on solving problems if you're demonstrating a solution up to a certain point. That work is correct, right? So you should get some credit for that. So if I were asking you to make a representation, and let's say in one of these, instead of 3, -1, 1, and 1, you wrote 3, -1, -1, -1, should you get partial credit for that? I mean, the fact that you could identify the dimensionality, that's a low-stakes reasoning problem. That one should be straightforward. And it's not a high point value. But understanding how to generate the characters correctly and the other components is more important. And maybe on some of these, you do come up with the right character. That's worth something. But you'll see later on in the class, if we cannot produce the correct characters for the representations, we won't be able to work out problems downstream, such as which spectroscopic transitions are allowed for this molecule, or which orbitals overlap in this molecule. So it will have a real meaningful chemical sense, but in order for us to extract the correct answer, it will require us to produce the correct characters in the representation. So in the first exam, that's exactly what I grade you on, is your ability to formulate the representations correctly, and then we'll learn how to work with these here in the next couple weeks.
And you mentioned that C, C2B, everything is their own class, like how?
So if you work out the similarity transforms for these elements in the point group, you only see the same element as a product of the similarity transform, which means each element is in its own class. However, there are many point groups that you will encounter where if you perform the similarity transforms, you will see that a number of the symmetry elements will be grouped together in the same class, because the similarity transforms produce every other element in the class. And then remember, the order of a class must be an integer divisor of the order of the group. Okay? So there are lots of point groups where you will see the order of the class not equal to 1. And we will start looking at those examples, but when we first illustrate the matrices that generate the characters of representations, it's always best to start with a simpler point group like C2V. Otherwise, we're combining too many tough ideas all in one, and we want to start from an easier idea and break out from that. Okay? All right, we'll see you on Wednesday.